Before I go on, let me just give you the what you'd have for Bernoulli in English units. You'd have pressure still. Now instead of newtons per meter squared, it'd be in pounds per square foot, for example. Weight density. Instead of mass density, you'll have weight density in the English system. And here you'll have weight density over gravity, because you've just got mass density. So in the English system, we take the weight density, pounds per cubic foot, we divide by gravity, 32 feet per second squared, and multiply it by the velocity squared. And that's constant. So how's this working, you might ask, except you're stuck inside that little camera and you can't. So let me give you an example. What I'll do is, we've got three terms. I'll only change two. So the first thing to figure out when you're solving a problem like this will be, hey, what's not changing? Makes the problem a lot simpler right away. So let's take a horizontal duct. And we'll expand it out. So I'm moving along here, and I've got water flowing through it. And it expands out to a larger area. I'll call this area 1 and this section 2. All right? The flow is going this way, and it's water, H2O. And I know the density of fresh water, or pure water, is 1,000 kilograms per cubic meter. And let's say the diameter of this first part is 3 centimeters. It's about like that. And the diameter of the second part, where expansion, is 6 centimeters. We'll double it up. So it expands out. And it's horizontal. So my first question is going to be, A, what's the velocity in the second section here? Well, to do this, I go back and I think about volume flow rate. Whatever happens, whatever volume flows in here, the rate at which it flows in, it's going to be the same as comes out here. If I've got 30 gallons a minute coming in this side, I've got to have 30 gallons a minute coming out here. It can't just disappear. So I use this. I say the volume flow rate, Q sub V in, QV1, is equal to the volume flow rate out, Q sub V2. Now if you remember, volume flow rate, it's volume over time, but it's also velocity times area. So what I'm going to do is I'm going to replace QV1, volume flow rate, with the equation velocity times area. Same thing. I'll say, okay, velocity 1 times area 1, that's volume flow rate 1, is equal to velocity 2 times area 2. That's the second volume flow rate. Now, I want to know what V2 is. I don't know these areas, but we can figure them out in a simpler manner. So I'm going to solve for V2. I'm going to divide both sides by that second area, and I'll get velocity 2 is velocity 1 times area 1 over area 2. Now, I could calculate the separate areas because I've got the diameters right here. But what I'm going to do is I'm going to put the equation for area in. I'll show you how it makes it simpler. It looks ugly at first, but here's my V1, velocity at 1, and instead of area is pi times the diameter squared over 4. So the first area will be pi times d1 squared over 4, divided by the second area, pi times d2 squared over 4. Now this is the good part. The pi's cancel, and the 4's cancel. So I never really had to calculate that whole thing. And this is going to be equal to velocity 1 times d1 squared over d2 squared, or just d1 over d2 squared. Now you can look at all that and you can just set it to pause if you want and make sure you have everything straight. Alright, so let's go from here and plug in the numbers. So that's equal to V1, which, let's see, I need to pick a V1. Let's go back over here and write down. Let's say V1 is 10 centimeters, or 10 meters, excuse me, per second. Try that. 10 meters a second. So I'll say, okay, I've got V1, 10 meters per second, divided by D1 over D2 squared, and that's times 3 centimeters D1 over 6 centimeters, and that's squared. I didn't even have to convert from centimeters to meters because the centimeters cancel out. Sweet. So this is going to give me 2.5 meters per second. Now, does that make sense? I started off here at 10 meters per second. I opened up the area. Volume flow rate's velocity times area. If the area goes up, velocity has to go down. So I got 2.5 meters per second. That makes sense. Now, let's use Bernoulli. The second part, let's say the pressure in the first part is 1 atmosphere. That'll be 100,000, or 1 times 10 to the 5th pascals. And a pascal is a Newton per meter squared, force over area. I want to know what's the pressure in that bigger area. So let's try Bernoulli's equation. I'm going to say that everything on the left, everything in the first section, is equal to everything in the second section. They're equal. Bernoulli's equation says all those terms, that sum of them is constant. So I'm going to say, well, the pressure in the first area plus gravitational potential energy density in the first area plus the kinetic energy density in the first area is the same as the conditions on the other side. It's equal to the pressure in the second area plus the gravitational potential energy density in the second area plus the kinetic energy density in the second area. This doesn't mean that each of these terms is the same as the other. Far from it. They can be much different, but the sum total is the same. We've just rearranged them. I mean, shoot, we already know that the velocity went down. So this term, this kinetic energy density term on the second side, it's going to be smaller. Now, what can we get rid of? I said it's a horizontal duct. Now, I've got pieces right here. If I've got flow coming in, some of the flow is going to be going up, some of it's be going down, but just as much will be going up as down, and so in generally, I don't change any height. So that means height 1 and height 2, the heights are the same in both sections, so screw it. They're the same term, I can just subtract them out. Now, if I want to solve or get a working equation for the second pressure, there it is right there. I've just got to subtract 1/2 rho V2 squared from both sides, and I'll have pressure all by itself, half my working equation. So let's try that. I'll get P2, the pressure I want, is equal to P1, the first pressure, plus 1/2 rho V1 squared minus 1/2 rho V2 squared. That's equal to 100,000, 1 times 10 to the 5th pascals. I'm going to write that as newtons per meter squared, plus 1/2. Now this rho, this density, it's 1,000 kilograms per meter cubed. I mentioned that at the beginning. 1,000 kilograms per meter cubed. And that's times the first velocity, 10 meters per second squared, minus 1/2 times the same density, 1,000 kilograms per meter cubed, times the velocity in the second section squared, which is 2.5 meters squared. Now, this is newtons per meter squared. This is 2. I've got kilogram, well, let's see, right here, I've got kilogram meters per second squared. Kilogram meters per second squared. That's a newton. So I've got a kilogram meter per second squared, but this is squared too. So I'm going to have an extra meter on top and a meter cubed on the bottom. This will cancel one of them. So I'll have a newton on the top and a meter squared on the bottom. Newtons per meter squared. So these are both newtons per meter squared too. If I put them together, do the calculation, let's see, this part's bigger, it's going to be bigger pressure. And so this is 1.49, and check this, do this calculation, see if you can do it, times 10 to the 5th newtons per meter squared, or pascals.